So open and closed traverses, and we're given a bit of detail about a traverse. A traverse is basically a walk that someone does, and they record different waypoints along the way. In this walk, someone started at point A, they measured the bearing of A to B, so from A to B is 62 degrees. It was 642 meters for them to get to point B. From point B, 091 degrees for a distance of 1089 meters until they get to point C, and so on until they get to point D. We're going to draw a scale diagram of this according to this scale. Okay, the distance in reality of the journey from A to B is 642 meters. We're going to convert this to a distance on the map. Okay, and I'm going to apply this scale factor. So 642 divided by 20,000. Okay, and that'll give me how many meters on my map I need to draw this thing. So I'll get my calculator. 642 divided by 20,000. Okay, so I get 0.0321 meters, or 3.21 centimeters. Okay, we can always, when we've got meters, times by 100 to make it into centimeters. So from here, I'm going to change these other two into map distances as well. I've calculated all of my distances, so I'm ready to go, ready to put them on the map. Okay, I'm going to start over here at point A, and I'm going to start drawing this traverse. So I know from point A, I'm going on a bearing of 62 degrees. Okay, I need to show where north is. Typically we'll just use the top of the page as north. Okay, and I want to go around at a bearing of 62. So I'll make sure I put my little crosshair in the middle there. Okay, and I'll count around to 62 degrees. Okay, place a little dot. Then I'll get my ruler out, and I'm going to go in this direction for 3.2 centimeters. So 3.2. There we go. Okay, I'm now at point B. I'm going to do the same thing now from point B at a bearing of 91 degrees. And 91 degrees. You can do some of this in pencil if you're not comfortable. For a distance of 5.4 centimeters. Okay, to point C. And then from point C at a bearing of 102 degrees. Again, go mark where north is. Direction 112 degrees. That's in that direction. And I'm marking 3.62 centimeters in that direction. Okay, up to point D. Okay, this is called an open traverse because we don't get back to the starting point. Okay, if I ask some follow-up questions and I said, for example, how far from D to A, okay, I should be able to measure this distance from D to A. I might just draw a light line in pencil. Okay, this distance on the map is 11.5 centimeters on my diagram. Okay, so I'd write on here, distance on map was 11.5, wasn't it? Yeah. The distance in reality will be that distance on the map times by the scale. Okay, so whenever we're trying to go from map to reality, multiply by the scale. So 11.5 times 20,000. Okay, 230,000, that's a pretty big number. To change it to meters, you need to divide by 100. 2,300 meters, or if you want, 2.3 kilometers. How would I find at what bearing it would be back there? So what's the bearing EA? Well, I could put a north line in here, get my protractor, line it up, and I want to know what direction it is all the way around to here. So I get like 269 degrees or thereabouts. Okay, just by reading it off. Okay, so that should give you a good idea of open traverses. Okay, we'll look at one closed traverse and see how we can correct it for error using Bowditch's method. Okay, following scale diagram shows a closed traverse survey that does not close. So we went from A to B, A to C, D, and then we're hoping to get back to A, but we're actually at this A1. We ended up on our map when we got back to the office, this distance away. So we're going to use a method to correct this survey. Okay, it's called Bowditch's method. What we'll do is start by just drawing a light line, and we're going to start measuring these distances for the survey. So I'll call this point A, measure how far this is, 33.9 centimeters, and I'll mark that on my diagram, and my little fixing diagram down the bottom. And then from B to C, we're going to do the same thing for all these points. Okay, there's point C, C to D, and D back to A. So the idea of Bowditch's method is all of the error didn't just happen from D to A. Okay, if we were really lazy and we just wanted to fix our diagram and make sure it was closed, make sure it's going back to the starting position, I'd just draw a line from D to A. A straight line between these and just fudge it. But we're going to fudge it a little bit more sophisticated. So this difference here, this 1 centimeter, I'm going to mark vertically here. Okay, this is my error. And what we're going to do is make a triangle here and draw little heights of each of these points. Which are going to allow me to spread the error across all of these little segments that happen. So at the same direction as the error, okay, I'll make sure it's as parallel as I can be. I'm going to draw little parallel lines in these directions. And I'm going to measure this little error at B, which is about 3 millimeters. And I'm going to mark that same distance along this line and call it B dash. Do the same thing for point C. That's like 0.6. You should be able to be a bit more accurate than me. And the same thing for D. 0.9. And then we can join these new dots. So the A is just going to remain the same. I'm going to go now to this new B point that I've made, to the new C point that I've made, to the new D point, and then I'll be able to go and close the survey. So if you look at all these directions, they haven't changed that much. So if you look from D dash to A, pretty much the same as that other path that we had. But since I've spread out the error through all of these points, slight changes in all of these paths, I've been able to close the survey without just having to fudge it at the end here from D to A. So the red line is the corrected traverse survey. And that was using Bowditch's method. So in conclusion, we can draw open traverses, okay, drawing scale diagrams, and we can also correct closed traverses that didn't actually close before. Try these questions. Okay, good luck.